Let's talk about an approach called agglomerative clustering. So looking at these two results that we might get from running k-means with different initial starting points for our centers, we end up with two different results. And they're very similar. In fact, the only difference between these two is that one leftmost point in the rightmost blob. On the left, it's colored yellow. And on the right, it's colored blue. So which clustering result do you like better? The one on the left or the one on the right? Well, if we asked k-means which one does it like better, well, the one on the right has lower inertia. So, okay, so its inertia is 87.28 versus the one on the left has an inertia of 94.41. So why is the inertia on the right lower? And is this the correct clustering or is it a wrong clustering? Because it has this blue point that's really near the set of yellow points. Well, think about it, right? Lower inertia means a smaller sum of the squared distances from each data point to its center. And so k-means really here is optimizing for inertia. That point off to the left is it's closer to the center, the blue center, than it is to the yellow center. So if we pair it up with the yellow center, it's going to increase the inertia. If instead we pair it up with the blue center, it decreases the inertia. But it makes our picture less blobby, right? The one on the left is a nice blue blob on the left and a yellow blob in the upper right. Whereas on the right picture, we have this like lone blue dot. And so is that clustering on the right wrong? Well, that's kind of a good question. It's also the perfect segue to agglomerative clustering. So when we looked at regression and classification, there were multiple different ways that we could do each of those. The same is true with clustering. There are many different ways that we can do clustering. Now we've looked at k-means, which tries to minimize inertia. The results, however, are not guaranteed to optimize the inertia. And even if we do reach some global optimum for inertia, it might not really match our intuition for what should be the best result. So let's look at a different idea. This idea is called agglomerative clustering. And it's kind of the natural way to do clustering is sort of the way to think about it. And if I had just started this lecture by saying, here's a set of points, try to come up with cluster of those points, it might be the way that you would probably come up with. Okay, so here's the basic idea. We start out with every data point as its own cluster. And then we're going to join clusters or merge clusters with their neighbors until we only have k clusters left. So let's see what this would look like for k equals 2. Okay, so now when the algorithm starts, every data point is its own cluster. So here we have 12 data points and we label them from 0 to 11. So we have 12 clusters. Now if we look at these points, we're going to merge by the closest cluster. And cluster 10, that singleton point, and cluster 11 are closest. So we're going to merge those two. So let's do that. So we put 10 and 11 into the same cluster. Now, because we have 12 clusters, that would be too many colors for you to try and keep track of. So I'm going to keep the numbers that are associated with the points. So when I merge 10 and 11, I'll call both of those 10. All right. So what are the next two closest points? Well, the next two closest points are going to be 0 and 4. So we'll merge them. And it might not appear completely apparent. It might look like maybe 3 and 4 are closer, but that's because we have different scales for the x-axis and the y-axis. 0 and 4 are actually the two closest points. So we'll merge those and we'll call that 0. Okay, so now at this point, we have 10 clusters, 8 that have a single point, 1 through 9, and 2 that have 2 2 points. So the cluster 0, 0 and 10, 10. So now, tricky question. If we look at all of these, or let's actually just look at a subset of these. If we were to look at cluster 0 and cluster 3, what's the distance? And the reason why I say this is a tricky question is because the cluster 0 has 2 points in it, while 3 just has a single point. So how do we compute? What do we compute? Well, what we could do is look at the distance between all of the points in each of the clusters. So in the case of 3, well, there's only 1 point. So we could look at the distance between 3 and the upper value of 0, the 0 cluster, and the lower point in the 0 cluster. And so at the end of the day, there's really no right answer, but a common choice is to use the maximum. Equally acceptable would have been to use the minimum or to use the average. And so here we're going to take the maximum distance, so that's the distance between 3 and the lower value for 0. But again, we could have used average, we could have used minimum, we could have used something else. We'll just take max. Okay, so now what are going to be our next two closest clusters? Well, it's going to be 1 and 5. So we'll merge 1 and 5, and so now we have the cluster 1. Okay, now our next closest clusters are going to be 7 and 9. Now, by looking at it, it doesn't look like they're the closest, but again, our x-axis has a different scale from our y-axis. Our x-axis goes up to greater than 7, while our y-axis goes up to 2.5. And so 7 and 9, trust me, are the closest two clusters. And so we're going to merge those. And so now we have the cluster 7. Okay, so now when we look at it, what's going to be our next closest cluster? It's going to be 6 and 8. Okay, so we'll merge 6 and 8 and have a cluster 6 that has 2 points. Okay, so now what's closest? Well, what's closest is going to be 0 and 3. So we'll merge 0 and 3. Okay, and so now that becomes a cluster of all zeros. Okay, next up, well, looking at this, that lower left set of clusters. So the cluster 1 and the cluster 10. So we're going to merge that, and that's going to become our cluster 1. So next up is what? Well, next up is going to be 0 and 7. Because if we take the highest point in 7 and the lowest point in 0, that's actually closer than our farthest point to the left in 6 and our farthest point to the right in 0. Even though the red line is looking shorter than the purple line, again, because we're on different axes for x and y, the purple line, trust me again, is actually shorter. And it probably would have been easier if I put these on the same axes, but then things would be really clumped together and it'd be a lot harder to see the full range here, especially because the x-axis is so much larger than the y-axis. Okay, so we're going to merge 0 and 7. Okay, so next up will be 0 and 6. And so we'll merge in 0 and 6, and we end up with a large cluster of 0. And then next up will be 0 and 2, and so we'll merge 2 into our cluster of 0. And so now we're done. K was equal to 2, and we have two clusters, our cluster 1 at the lower left and our cluster 0 at the upper right. Now, I was actually doing this using real points from our iris classification data set, and so we could look at the full data set and what will result. And what we see is we get the output of a cluster on the lower left, that's 1s, and the cluster on the upper right, that's 0s. And so if we apply colors, we end up with yellow at the lower left and blue at the upper right. And so agglomerative clustering, we don't have that blue point off by itself. And so again, it still is this question of where should that blue point belong? Should it belong in the yellow cluster or should it belong in the blue cluster? If we do this kind of natural agglomerative clustering, it makes sense for it to be in that right cluster. But if we're looking at a loss function of sum of square distances from the center, then it belongs to the left. So this type of agglomerative clustering approach, it's known as hierarchical. It's a form of hierarchical clustering. And if we keep track of when two clusters got merged, then each cluster becomes a tree. And we can visualize that merging hierarchy. And that results in one of these dendrograms. We saw one of those like the one on the right at the beginning of the class. And here you can see it again. And it's oftentimes, you may be able to learn something about when something gets merged into a cluster may be significant. And the sizes of the clusters may also be significant. So I'm not going to talk about this any further, but you may run into these, depending on what field you're in, you may run into dendrograms in the future. Okay, so remember I said there are lots of different clustering algorithms. So there's a huge set of clustering algorithms. Here are some of the algorithms that are implemented by scikit-learn. We just looked at two of them. We looked at k-means and we looked at agglomerative. But there are many other types of clustering algorithms that you could use. And here we see a variety of different data sets and how each of those data sets colors the clusters. And the one I think that's probably the most interesting is the third one down from the top, where you see those point clouds. And there you can see, k-means clusters that center cluster part green and part yellow, while the agglomerative approach colors it only blue, and green is only the blob off to the right and yellow is the blob off to the left, which is the right approach, right? Agglomerative takes into account that there's a little gap between what it calls the green cluster and what it calls the blue cluster. But with k-means, we're just looking at the centers and the distance from the centers. And maybe that little gap is actually not significant. That might be some measurement artifact. And so, again, it's very subjective. It can be very subjective which we pick as the best approach. Sometimes, however, this can have real-world consequences. So here's a little quick sidetrack of grading. Now, some professors choose to use agglomerative clustering for the grading bins. So they say if there's a big gap between two people, then you draw a grading threshold there. And so their idea is that you want to have grade clustering that looks like what you see on the left, not what you see on the right. So I'm actually not one of those people. I tend to take an approach where I look at what makes sense in terms of the grading bins. And then it may be the case that the grading bins fall where there isn't a natural gap. So again, which is the better approach? Should you draw big gaps, draw the bins at the gaps, or should you draw the bins on a distribution? It's subjective, and it's up to you to decide, which makes the most sense for a particular problem. My point here is that there are multiple different clustering algorithms, and there are multiple different things that you can try to optimize with each clustering algorithm.